Hi, my name is Valerie, and today I'll be talking to you about my work on studying Intel Optane DC persistent memory for the parallel processing of large neuroimaging data. So what does neuroimaging big data look like? Well, these are just a few examples. We have the Human Connectome project, which aims to map the entire human connectome of many different individuals, and it is expected to reach 1 petabyte in size. We have the UK Biobank, which is a large-scale study on the determinants of diseases, and it is expected to reach 200 terabytes of neuroimaging data. And we have the Big Brain Project, which is a one-of-a-kind histological image of a human brain. It is currently at 20 micron resolution and reaches 603 gigabytes in size. There are efforts to increase it to a 1 micron resolution, which is expected to be about 1 petabyte in size. So we have all this data, and moving this data around can incur significant cost. And so there have been various different solutions in place to address these data transfer costs. So first, kind of baseline way to reduce the data transfer cost is through the kernel, so via the Linux page cache. When you read data, if that data has been read before and remains in cache, that is a cache hit, and you will only pay the memory bandwidth when reading that data. If if there is a cache miss, that it means that the data is not in RAM, you'll be reading that data directly from storage device, and so incurring the slower throughput cost. In contrast, there's the write, and for writes, what happens is that when you write data, it'll be written to memory if you have write-back cache enable, and that data will be asynchronously flushed to disk. And so your application will only pay for the memory throughput, but not necessarily for the disk throughput, depending on the amount of available memory you have. Big data engines and file systems have addressed these issues further by implementing things, strategies such as data locality, that is, move the task to where the data is rather than moving the data around. And they've also implemented in-memory computing. DRAM is faster than other storage devices, so keep the data in memory whenever possible. You can also reduce the data transfer costs by adopting higher throughput storage. So we have a hierarchy of different storage devices, from volatile memory to persistent memory, and then slower would be SSDs, different types of SSDs, HDDs, network storage. And so for this study, we'll be looking at Intel Optane specifically for the processing of neuroimaging data. And so what is Intel Optane? Well, it's an affordable high-performance storage technology. Right now, it provides more memory that can be possible with DRAM, and it is also a cheaper alternative to DRAM. It is available in 128, 256, and 512 gigabyte formats, and provides two different configuration modes, that is memory mode and AppDirect mode. So what is memory mode? Well, it enables Optane to be an extension of your available memory. That is, it operates just like DRAM would. It is a volatile storage device, which means that you'll lose the data should your system restart. The nice thing about it is that it can use available DRAM as cache. So DRAM is just a tier above in terms of performance, and by using DRAM as cache, you can get better performance from Optane. The other configuration is AppDirect. So AppDirect contrasts memory mode in that it is non-volatile, which means that you can persist memory to, or persist data to the memory module. And it's accessible just like you would any other storage device. Applications can interact with it using POSIX, open, create, read-write calls. In the case of app direct mode, it is possible to disable DRAM as cache. So what we'd like to do is we want to quantify the added value of Optane on neuroimaging pipelines. There has been no other study, well, our study was one of the first to address neuroimaging pipelines. The second is to determine which configuration memory mode or app direct is preferable. So we devised a performance model to help us better understand the different storage devices. So basically we described makespan as being greater or equal to the sum of the time it takes to read the data and the time it takes to write the data. So here we're assuming that there is negligible CPU time. In reality, it'd be plus CPU, which is why we said that makespan could be greater than the I/O time. Now, one thing that's kind of important to note is that we assume the read and write bandwidth of one device. However, in distributed or parallel file systems, there would be multiple devices attached, and therefore makespan could be a bit lower than our estimate. And so for our study, we had two applications. Our first one is the big brain incrementation. So we took the full image, which has the full 76 and 603 gigabyte image, and split it up into 125 and 1,000 blocks. And what we did was for each block or chunk, we read the chunk from a given file system, which could have been TempFS, Optane, local disk, which is the SSD, or Asylon. Then I'd take that block and increment each voxel by 1. And then we'd save that chunk to the respective file system. We used two different frameworks for this. So we had GNU Parallel and Apache Spark. We also varied the number of processes. So we had 25 and 96 parallel processes. And we used TempFS, Optane, SSD, and Asylon, and compared each device with each other. Our other application was the BIDS app example. So the BIDS app example pipeline is just a template for how to build applications that conform to the brain imaging data structure. But this application uses or performs brain extraction using the FSL-BET application. And this application in itself is very frequently used in neuroimaging pipelines. As our data set, we took the entire Consortium for Reliability and Reproducibility data set, which is nearly 1 terabyte in size. However, the brain extraction pipeline only processes a subset of the data, which consists of the anatomical images, and that would have been approximately 39 gigabytes. We parallelized this application using GNU Parallel with 25 and 96 processes on both configuration modes, and on Optane and SSD and Asylon, where the SSD and Asylon were only configured, were only benchmarked with memory mode and not with app direct. So for our experiment, we received a server directly from Dell to perform this study. It had Red Hat Enterprise 7.6 as an operating system and 2 Intel Xeon CPUs with 768 gigabytes of DRAM and 3 terabytes of Optane. It additionally had 240 gigabytes of SSD and 720 terabytes of Asylon storage. So we benchmarked all the available or all the storage devices that we would use, and that could be seen on the table on the right. And we can see here that our benchmarks for our bandwidth for Optane was very close to DRAM and significantly faster to the local SSD that we had access to. So for our first experiment, we looked at big brain, 776 gigabytes, so the smaller image, using new parallel and 25 processes. And what we notice is that DRAM outperforms all other available storage devices. Optane in memory mode is very close to DRAM. In fact, it's almost identical. But we notice that AppDirect is actually 12 times slower than Optane in memory mode. And we can see that Sasson is by far the slowest device, with it being 120 times slower than other devices. We then compared the total read, increment, and write breakdown for each storage device. So Optane in memory mode performed about the same as DRAM, but we noticed that in AppDirect mode, we had 7 times slower reading compared to memory and 23 times slower writing compared to DRAM. And in contrast to that, when we looked at the SSD, the read time was very large, which is normal, as we'd assumed that reading would be rather slow. But however, the writes are surprisingly fast. And that we can assume is that all the writes were able to be done through the page cache, whereas the reads, because we were reading a new file and each time, it wouldn't have been in cache, and so it would be slow. And then what's interesting is that for Sasson, the read time was actually slower than SSD, and that's probably because the Sasson is a more scalable device than our local SSD, which is just one device. And then when we looked at the Gantt charts for each different storage, we noticed that the average concurrency on the SSD and on Optane was the highest, followed by DRAM, which had a 17.2 parallel tasks and finished very rapidly, and Sasson, which was the slowest and had 14 parallel tasks on average. And we can see that it's because the tasks were very much distributed. And then we increased the number of processes. So the same data set with new parallel, but 96 processes this time. And so when we looked at the make span, we noticed that there was no reduction in make span compared to the 25 processes. And then when we looked at the breakdown, we noticed that the total read and write durations were almost 4 times greater for each storage device, with the read in AppDirect mode being 6 times slower and the write being 2 times slower. And then we looked at the Gantt charts, and we noticed that we can see that in memory mode, the read and writes were very quick, whereas in AppDirect mode, both the read and the writes took a significant amount of time. And it's probably attributed to the fact that AppDirect mode was not configured to use DRAM as page cache in our case. When we processed the full big brain, or the highest resolution big brain data set, so the 603 gigabyte one with new parallel at 25 processes, what we see is that the real performance, so what's in gray, is usually lower than what our model has estimated. And when we looked at compare to Sasson memory mode to AppDirect mode, we didn't see that the modes actually cause a difference, whereas there was a difference between Optane in memory mode and Optane in AppDirect mode. When looking at the breakdowns, we noticed that, as before, Optane AppDirect mode has 12 times more writing time than memory mode, and we notice that when comparing Cylon in both modes, that AppDirect mode is approximately 1.4 times slower for the reading and incrementing. And then, so same data set, 25 processes with Apache Spark. We noticed that Apache or Spark is actually closer to, like, the results for Cylon, they appear to be closer to the model estimates. And when we looked at the breakdown, we noticed that the total write duration was longer with Spark than with New Parallel. And then we increased the number of processes, but stick with New Parallel. And we noticed that Optane was about 1.3 times faster at 96 processes than it was at 25, with Cylon being about 1.1 times slower at 96 than with 25. This is probably because there is more increased contention on Cylon, but it shows that Optane can scale very well. And we notice that memory mode is superior again for Optane. And so AppDirect mode was still a bit slower than memory mode. And when we looked at the breakdown, we notice again write time is still significant and is very significant for AppDirect mode, Optane and AppDirect mode, and Cylon. When we looked at Apache Spark at 96 processes, we noticed that the makespan is similar between memory mode and AppDirect mode for Optane. And when we looked further into this, we noticed that Spark was actually spending a lot more time in garbage collection with memory mode, and that's likely because Python objects were able to persist in memory and ended up on Optane as they were unused. Which is a slower device than memory, and so garbage collection took a bit more time. And then when we looked at the breakdown, we noticed similar trends as before. Write time is significant. And here we noticed that Spark was faster than New Parallel for writing. And then we looked at our second application, so the BIDS app one, and we compared the makespan between 25 and 96 processes. In this case, we noticed that AppDirect mode is slower than disk in both 25 and 96. Now, our data set was rather small, and all the data could fit into page cache. And so we believe that local disk actually benefited a lot from page cache here, whereas AppDirect mode, which was not using the DRAM cache, ended up paying a penalty for not using it. We also noticed that the performance was improved with increased parallelization. When we looked at the breakdown, we noticed that both I/O and CPU increased with increase in processes, and that's because there's more contention in the case of I/O on the storage devices, so it is normal that I/O time increased with more processes. So overall, we found that the configuration mode didn't affect the performance of other storage devices. However, this might not necessarily be true in all cases. If significant amounts of memory are being used, more so than the amount of available DRAM, other storage devices will likely start to feel the performance penalties of having a slightly slower storage device such as Optane. However, the amount of memory would not otherwise be accessible without Optane, so this is not a significant problem if you're processing large amounts of data. We noticed that in all cases, memory mode offered a better performance to app direct mode, and that's likely because it was using DRAM as cache. We also noticed that memory mode was with Spark was slower, and that's likely due to garbage collection of objects that are stored on Optane rather than DRAM. And we conclude that performance to scalable network storage, such as Cylon, could be improved with Optane. Say, if we use Optane as a burst buffer to Cylon, then we would likely observe a very high speed up in that reading and writing of files to Optane. And we also believe that it's beneficial to the visualization of high resolution neuroimaging data, which would require significant amounts of memory. Thank you.